Hi everyone, thank you for joining us. This is a talk about scalable XGBoost on GPU clusters. I'm Jiaming Yuan, one of the current maintainers of XGBoost and currently working for NVIDIA as a software engineer. My colleague Bobby and I will cover some of the latest development and future directions for the library XGBoost. Welcome. So I will give a brief introduction to XGBoost at first, and then we'll cover some of the latest features and future directions, including categorical data feature support and multi-output models. So after that, I will give a comparison for the GPU acceleration and share some details on its latest status for running XGBoost on NVIDIA GPU. After that, Bobby will give an introduction to the Spark package of XGBoost and share some details on how to scale XGBoost on GPU clusters. Yep. So, all right, let's get started. XGBoost is an open source gradient boosting library that focuses on decision tree models. Gradient boosting is a well-known algorithm for machine learning pipelines and practitioners. It has wide application. So XGBoost is an implementation for that algorithm. So it supports regression, classification, learning to rank, survival training, and other types of model if you can define a custom objective. So basically, you can define a custom objective and make your own model types. One of its design goals of XGBoost is to be as efficient and as scalable as possible in order to handle large data size. So yeah, that's one of the reasons that we need Spark package and also the GPU support. So by itself, XGBoost is only a machine learning library. And what the user wants from training is to get a model that can be used in other places, like online inference. And that's the most important part of machine learning. So XGBoost has a reusable model format. It can be saved as JSON or UBJSON. So the latter is just a binary version of the former. You can get a full specification for UBJSON online. Also, XGBoost supports slicing the model. So to give you an example, if you have 4 trees trained by XGBoost, you can extract the first or the second trees using XGBoost. So in previous versions of XGBoost, it supports only numerical data. And in practice, we often see categorical data that's widely used in many applications like stock prediction. And in the latest XGBoost, we started the experimental support for categorical features and also multi-output models. And we will talk more about those new features and their future direction. Yeah, this is a brief introduction. Yep. XGBoost has many features. So these are some of the timelines for the library development. And these are the features that we'll focus in this talk. And I hope everyone enjoys it and find it useful. All right, let's get started with categorical feature first. Categorical feature is often seen in tabular datasets, but less often in other types of data. So for example, if you are doing image processing, then it's numerical data, RGB is continuous. And there are many techniques for handling categorical features, so we can primarily categorize them into 2 types. The first one would be feature engineering, and that includes both one-hot encoding and target encoding. These encoding techniques are most well known. Another type of support is that to handle the categorical feature by machine learning training model, training algorithm itself, and we can build a machine learning model that specifically handles categorical feature. So one of the best models for categorical feature is decision tree model. So on the bottom right corner, you can see an image that is a small decision tree. With that decision tree, we can ask it to split the nodes in a way that, so for example, we can ask it to put certain categories to the right branch and the rest of the categories to the left branch. In this way, we can build a complete decision tree using only categorical features. And also, we can mix it with other types of feature like numerical feature. In XGBoost, the feature is quite new, and this talk is about latest status and future direction. So right now, XGBoost 1.6 as shown in the previous slide, the timeline slide, and we have supports for two types of algorithm. The first one is one-hot encoding, and the second one is optimal split. We will get started with one-hot encoding first. So the name one-hot encoding is a technique for feature engineering, right? So why do we need to build it inside the model training algorithm? So to give you an example, if you are using, for example, the one-hot encoder from scikit-learn, and it given a categorical feature, it returns a sparse matrix that has many zeros in it. And that means we might increase the memory usage and reduce the computation efficiency significantly, especially if you are embedding those features into a dense matrix. So yeah, that's when XGBoost, the one-hot encoding training comes in and to help you to reduce the memory usage and to increase the computation efficiency. So the second supported algorithm is optimal split. So for one-hot encoding, the tree training algorithm would pick one category for each split and for the right branch, and then the rest of the categories to the left branch. So in this way, we have, if we want to go over all the categories, and we have to build really deep tree, and that means a large model, and it might converge slowly. So unlike the one-hot encoding, we support optimal split, which means we can partition the categories into two sets, and one set for each branch of the decision tree. In this way, we can have multiple categories for each tree split, and we can converge much faster. And the way that we can split these categories is mathematically proven to be optimal, is a well-established technique used in decision tree. It was brought into the context of gradient boosting by another implementation called GPM, which is now also supported in XGBoost. So using this technique, the training pipeline can usually converge much faster and build smaller model. So why do we need to support both of them? So one of the reasons is that the optimal split has a catch. So it's optimal, that means it's subjected to overfitting quite easily. So if you think about it, how many possible ways you can partition a set of categories, that's exponential, right? And that means the search space is extremely huge, and you might get a model that's overfitting your data. So as a complete solution for categorical datasets, we provide both implementations, and users can choose the one that fits their own need. And we will leave the parameter tuning to the users to based on their own datasets. So another thing I want to mention is that XGBoost support full pipeline on GPU that includes categorical features. And that means you can have your categorical features in the training pipeline that runs naturally on GPU. So for example, if you have a data frame that is stored in QDF, if you have a QDF data frame, that means it's resided on GPU, and XGBoost can take that data frame directly and use the categorical features in it without any CPU activities. Yeah, I share some of the reference on this slide, and you feel free to take a deeper look into them. And XGBoost is a open source library. You can also ask questions and issues on GitHub. Yeah, we don't have live coding here, and so I will show some code snippets around various features of XGBoost. Yeah, this is about using categorical features with XGBoost. So it's quite easy if you are using Python. The first step is to use the data frame, either QDF or pandas, and set the features that are categorical as the category type, and then supply it to XGBoost. So by any chance, if you are already familiar with the circular interface of XGBoost, then this should look familiar with you. And all you need to do is to specify the parameter enable categorical equals true to inform the XGBoost that it should handle those values as discrete values. So after that, it's pretty standard scikit-learn stuff. You can just copy on X and Y. One catch here is that XGBoost requires the new model format JSON or UB-JSON to be used with categorical feature. And yeah, that is a requirement, and that can be easily done with specifying the file format as JSON or UBJ. So yeah, XGBoost by itself is just a machine learning library, and it produces a model, and we usually want to use it somewhere else, like online inference or model explanation, or we use the model to pick the most important features, and that requires a larger ecosystem. And right now, we have two libraries that can directly load the XGBoost model. So the first one is Treelight, another one is Phil, which is part of QML. On the right-hand side, there is a small example for how to use QML for fast inference. And I share a link on the bottom. You can take a look into their documents and their examples. They have plenty of them. Yeah, so this talk is about latest development and future direction. So I will also share some of the future work for XGBoost. And so if anyone is interested in this part, yeah, feel free to talk to us on GitHub, on any other public channels. So one thing that is going on is for sparse data handling. And if you have sparse data, which means your data has missing values, then you need to use the latest version of latest development branch of XGBoost. So also, as I mentioned, the optimal split is subjected to overfitting. So we are adding more parameters for regularizations. Yeah, right. So another exciting new feature we want to share is the multi-output support. And there are many multi-output models. So most basic thing is multi-class classification, which is already supported by XGBoost a long time ago. And there are other types of multi-outputs, including multi-target regression and multi-label classification, which is just another name of multi-target binary classification. And lastly, it would be multi-target multi-class classification. And so right now we have added the multi-target and multi-label for XGBoost. On the slide, there is a small example for how to use multi-label classification, and that is pretty standard scikit-learn interface. So if you have used XGBoost before, then there is no code change or no new things that you need to do. You just put your data in and XGBoost will understand that you want a multi-target model. Yeah, so for the current support status, what XGBoost does can be simulated by some other methods. For example, you can use the meta estimator from scikit-learn to define a multi-target model. I think the name is multi-output regressor or something similar. So why do we need to do that in XGBoost? Yeah, so one of the primary reasons is that we can make the computation much more efficient than using the meta estimator directly. We can skip creating many internal data structures inside XGBoost. Another advantage of doing it inside XGBoost is for better feature integration. So users can specify their own custom objective for multi-target model, and they can specify callback functions, and they can define their own advanced early stopping strategies. Also, we have more plans for this feature. Yeah, this is also about feature direction. One of the things that we want to do in the future is for handling correlated targets. So right now for multi-target models, if you have multiple targets, XGBoost assumes it to be independent, which might not be desired. There's also an assumption of scikit-learn estimator, and you want to handle correlated targets better in the future. Another thing is handling sparse targets. So for multi-label classification, your input labels might contain multiple zeros, and we want to skip those zeros for better memory usage and better computation efficiencies. Right. Yeah, so after the introduction for new features, we also want to talk about GPU acceleration, which is a big part of XGBoost. Yeah, if you look into the code base, at least 1/3 of the code is about GPU. Yeah, one of the strengths of XGBoost is that it can run everything, the whole pipeline on GPU. That means it consumes GPU data and output GPU data. You can train the model completely on GPU for all kinds of tasks. You can do inference with GPU input and output directly a GPU array or GPU data frame. You can run sharp value computation on GPU, which is much faster, and we'll share the benchmark in next slide. You can do evaluation like AUC, PRAUC on GPU. And unlike some other libraries like neural network implementations, they might not obtain deterministic results. So for example, it might be caused by non-determinism in the matrix convolution or matrix multiplication. XGBoost can output deterministic result and is mathematically proven. Lastly, XGBoost can run on MNMG environment. That means multi-node and multi-GPU. We'll talk more about distributed environment later, and especially around the Spark framework. So yeah, the one thing I want to talk about XGBoost GPU support is not its internal, but rather its integration with the whole GPU ecosystem. If you look at this stack, you would find some other CUDA-based libraries, including Rapid Primitives and CUDF QML, and XGBoost is well integrated with all these other libraries. So to give you an example, if you have a QDF data frame that is used for feature engineering, XGBoost can take that data frame directly and XGBoost understand the arrow format. And also, XGBoost and GramL and QDF can share the same GPU memory pool based on rapid primitives, and specifically that's RMM. Yep. So on this stack, we show only the single node model, and we'll extend this stack later to distributed frameworks. Yeah, one thing about GPU support that sometimes people find inconvenient is that most often XGBoost consumes too much GPU memory. So, and GPU memory is also more precious than CPU memory. So the problem is that gradient boosting is not a stochastic algorithm. So many people came from deep learning, and they are so used to training the models batch by batch, and all of a sudden that is gone, and their data cannot fit into GPU. So yeah, that's a algorithm's problem, but XGBoost makes some specific optimization for GPU memory usage. So there is a data structure called device contidy matrix, and which can consume GPU data directly without making any copy or creating any internal data structure, and it can take the data as it is. In practice, we can basically shrink down the memory usage by half. Another optimization we do in XGBoost is in-place prediction, which means XGBoost will consume your data directly and understand the data's format. So for example, if you have a CUDA array or you have a QDF data frame, XGBoost can go into those arrays or data frames directly without making any middle structures. So in this way, users can have as much data as possible. And as we all know, data is basically the backbone of machine learning. If you have bias and variance problem, the best solution is to provide more data. And that's what we want for XGBoost, to handle as much data as possible. Yeah, I will show some performance comparisons in the next slide. And this is about what are the platforms that we use for those comparisons in the next slide. So we compare the GPU implementation with the CPU implementation on V100, and also the CPU implementation is running on 40 CPU cores without hyperthreading, so they are physical cores. We use the max depth equals A parameter to limit the model size, and also we use the depth-wise growth policy. All this hardware is on NGC, the NVIDIA Cloud Servers. So you might notice in the next slide, the datasets for SHAP comparison are smaller, and that's because we have limited time and we don't want to run the benchmark for too long. And we'll show the performance for SHAP contribution, but not interaction, because without a GPU, the interaction is gonna run forever. Yeah, you can try it yourself. And the interaction, the acceleration of feature interaction on GPU basically put it from impossible to usable. Yeah, this is a comparison for GPU and CPU. And on the x-axis is the name of dataset, and on the y-axis is the times of GPU speedup. Yep. The code for producing these benchmark results is openly available, and users can try to reproduce the result by themselves. All right, let's talk about distributed XGBoost. And yeah, we are building things up. We talk about GPU, and then we talk about distributed XGBoost, and then we'll talk about distributed XGBoost on GPU cluster. Yep. XGBoost is integrated with many distributed frameworks, and so it has Spark DAS interface, and it has Spark interface. It also has Array interface, but we'll focus on Spark in this talk. As mentioned, XGBoost is designed to be efficient and scalable, and it has many specialization for distributed environments that range from training to evaluation to prediction. So to give you an example, during evaluation, the computation of AUC is quite difficult because we have a sorting operation inside the AUC, and we make approximation for distributed environments for both ROC and PR, and that's just an example. We'll talk more about them specialization later. So here is a snapshot for how to train XGBoost on distributed environment. On the left-hand side is the DAS interface, and on the right-hand side is the Spark interface. So it's by design that we make it as similar as possible to the single node interface, so that user can scale up their pipeline easily. Yeah, this is the stack for XGBoost distributed on GPU cluster. Based on previous stack I showed in the previous slides. On top of Python, we have Dask, and if you use Spark, then on top of Scala, based on the same stack here, you have the Spark package for XGBoost. So this is another specialization. So one of the most important thing about distributed training is that we need to handle more data. And for most of the distributed frameworks, like Spark and Dask, they handle data in chunks. But as I mentioned previously, XGBoost is not a statistic algorithm, and it needs the whole dataset available on memory. That means we need to concatenate all those chunks from distributed frameworks before we can start training. So we make a specialization for this environment, and right now, XGBoost can consume GPU chunks directly without the concatenation, and as a result, it can avoid making data copies. The feature is enabled for both Dask and Spark, and yeah, you can try the Spark package and use the device contact matrix in that package. And as a result, we want XGBoost to handle as much data as possible, so don't hesitate to get more data. Yeah, I will hand it over to my colleague Bobby for distributed Spark XGBoost on GPU clusters. Thank you.
Thanks, Jiaming. This is Bobby Wang speaking. I'm a software engineer and innovator. Today I will give the topic about running XGBoost on Spark with the GPU acceleration. So before diving into the GPU acceleration, let's go through a recent important change about the battery execution mode. Previously, XGBoost has its own logic to handle some unexpected situations by keying Spark context. But it's really not a good user experience. So we have introduced the Spark battery execution mode, which should resolve this issue, and it will make XGBoost stable and robust. So let's get back. To XGBoost for Spark GPU. XGBoost for Spark GPU is an open source library for accelerating distributed XGBoost training on Spark. It has the ability to use the rapid accelerator to speed up the end-to-end GPU acceleration. We already have the XGBoost for GSpark project. So why do we still need the XGBoost for GSpark GPU? Well, the XGBoost for GSpark does not support a GPU. So while the XGBoost for GSpark GPU extends the XGBoost for GSpark Spark and is able to use the rapid accelerator to enable the whole GPU pipeline, including ETL and training. We have mentioned many times about the rapid accelerator. So what is the rapid accelerator and what the rapid accelerator can do? So with these questions, let's go through the rapid accelerator quickly. Right, in a word, the rapid accelerator is to leverage GPUs to accelerate the data processing while the rapids libraries. So why XGBoost leads the rapid accelerator? From the machine learning workflow, if you are working on the machine learning, you probably know that training model and doing the prediction is just a small portion of the whole work. Most of the time will be spent on the data preparation because it has not been accelerated by the GPU. While the rapid accelerator can just speed up this part, so that's the reason. Rapid accelerator not only speeds up the Spark Circle data frame API, but it also supports the Spark Shuffle process. This slide shows how XGBoost is accelerated by rapid accelerator. First, the rapid accelerator loads the data from the cloud into the GPU memory, and then does some, transformations on GPU. And after the data is prepared, XGBoost began to construct the quantile metrics on GPU. Finally, doing the training on the GPU. So you can see everything is running on GPU. It should be pretty fast. In order not to change any code to use the rapid accelerator, we have introduced the new API, state features column, which accepts an array of feature column names. The new API can also be used in XGBoost Spark project. So with the new API, users do not need to change any code to run below code on CPU or on GPU. We have compared for different XGBoost trainings on Spark. CPU means CPU loading and CPU training. CPU-GPU means CPU loading and GPU training. GPU-GPU means GPU loading with the rapid accelerator and the GPU training. DB-Python is the Databricks XGBoost PySpark wrapper, which is the same as the CPU loading and the GPU training. The only difference is it is based on the XGBoost Python package instead of the XGBoost JVM packages. We ran the performance on the Databricks cluster with the below configurations. Because the Databricks solution does not support the fractional GPU, so we must set the Spark task resource GPU amount to 1. But it will limit the task parallelisms, which means in this case, there will only be 2 tasks running at a time. Anyway, from the test result, we can see the GPU has 9.2x speed up than CPU and 5.2x speed up than GPU and 4.8x speed up than DB-Python. The performance for the CPU and DB-Python is pretty close because both of them are using the CPU loading and GPU training. Setting Spark task resource GPU amount to 1 may be unfair for the CPU loading. So in this case, we just exclude the Databricks solution and set the Spark task resource GPU amount to fraction. With this setting, which means there will be 16 tasks running for the XGBoost ETL stages at a time. So from the test result, we can see the GPU still has 5.2x speedup than CPU, and 4.1x speedup than CPU-GPU. The performance is impressive. We have packed the details on how to reproduce the performance for XGBoost for the Spark GPU in this reference. So users can, check it out and reproduce it by yourself. That's all from my part. Thank you.
All right, thank you, everyone.
Thank you.